Good morning all. So in our last class what we have seen is the derivation of work done, that is potential difference. What do you mean by potential? We have seen what do you mean by potential, line integral form of that, right? So in this particular class let us write the equation for potential, okay, then potential field due to point charge, line charge and different distribution of charges. Okay, let us go with potential equation. Electrostatic potential at a point. We have seen the equation for work done, that is W is equal to minus Q integration from A to B E dot dl. This is the equation which we have derived in our previous class, right? So this is the equation which gives the information about a unit positive charge Q pushed from point A to B in a constant electric field in opposite direction. Okay, the work done is given by this equation. Now by using this equation we can deduce this equation to the potential, electrostatic potential at a point. How? When this charge is unit positive charge of 1 coulomb, then point A is at infinity and point B is at particular point P. Then what happens to this equation? Then W becomes V, work done becomes potential V. Then V is equal to minus Q is 1 integration from infinity to B E dot dl. That's it. This is the equation for general equation. Then this B becomes general point P. Then V is equal to minus of integration from my infinity to P E dot dl. Okay, this is the equation for potential at a point. Potential at a point. Okay, let us continue with our next topic, potential field of a point charge. Now what do you mean by potential field? We have derived the equation for potential, electrostatic potential. Now what is this potential field? So potential field is a region or space wherein an electric potential could be assigned to each and every point in it is called as potential field. Potential field. This is the definition of potential field. Let me read again. Region or space wherein an electric potential could be assigned to each and every point in it. In it means in that particular region or space is called as potential field. So how to calculate potential field of a point charge? Okay, for that we need to consider a geometry. Consider a point charge Q. Consider a point charge Q at point O. This is the point charge of Q coulomb at point O. consider two arbitrary points A and B. Okay, so let it be B and this is A. Consider two arbitrary points A and B within the vicinity of the field developed by this charge Q. Within the vicinity of the electric field developed by this charge Q. As the distance increases from this point O, the electric field decreases, right? So point B is at distance RB from O. Point A is at distance RA from O. We need to push a charge from unit positive charge from A to B in an arbitrary direction. We need to push a charge from A to B in an arbitrary direction within the given electric field. Okay, consider a point P. Consider an arbitrary point P on the path of AB, which is at a distance r from the origin. Which is at distance r from origin. Okay. Now, the electric field E is coming out in this direction. Got it? Now, consider a differential length. Consider a differential length delta L. That is, the point P, the charge at point P is moved further with a length of delta L. Okay, this is the differential length at which charge at point P is moved towards B. So which forms the length R plus delta R. R plus delta R. This is the length which we have given. Okay, now which forms an angle theta. So let me write here, this is the length delta L, which forms an angle theta with respect to the path. Okay, now this is, name this point as R. This point as R. Now draw a perpendicular to OR. Draw a perpendicular to OR. Okay, this is 90 degree. This point is named as M. Okay, draw a perpendicular MP to OR. Draw a perpendicular MP to the line OR. Now OP is the distance between point charge Q and point P. Then OR is the distance between the differential length traveled by the unit positive charge and origin. Okay, now assumption is very simple. Since delta S is very less, since delta L is very less, OP and OR are approximately equal. Okay, since delta L is very small, OP and OR are approximately equal. Therefore, MP is also perpendicular to OP and OR. The line MP is perpendicular to OP and OR. So with this assumption, this angle also becomes theta. This angle also becomes theta. Then what about this distance? This distance is delta R. MR, the distance MR is equal to delta R. Now, how to derive the equation for this distance? We know this angle is theta. What we need, this distance MR, we can write like this, right? Cos theta is equal to mr divided by delta L, adjacent by hypotenuse. Hypotenuse is delta L. What is mr? Mr is equal to delta r divided by delta L. What we need? What is the equation for? We need delta r is equal to delta L into cos theta. So let us keep this aside. Okay. Now this is the unit positive charge placed at origin. Now in order to push this charge from P to R, we need to perform some work. That work done is delta W. Elementary work done is delta W. That is given by minus E dot dl. Minus E dot dl. Elementary work done by pushing a charge from P to R is given by delta W is equal to minus E dot dl. Now if we expand this expression, delta W is equal to E into dl into cos theta. We know the expression for dot product. Dot product between any two quantities is given by this equation, E into dl into cos theta, right? Okay. This is not dl, this is delta L. Delta L. Okay. Now delta W is equal to minus, what is the expression for E? Q divided by 4 pi epsilon naught into R square into delta L into cos theta. What is delta L into cos theta? Delta L into cos theta is delta R. From the above equation, if we substitute like this, minus Q divided by 4 pi epsilon naught into R square into this quantity can be written as delta R, right? This is the elementary work done. Now in order to push a unit positive charge from A to B, we need to integrate all the elementary work done, right? That is, the total work done W is equal to integration of all the elementary work done components, that is minus of integral of Q divided by 4 pi epsilon naught into R square into delta R. Now we know that as delta L tends to 0, then delta L becomes dl. When dl becomes, then delta W becomes dw. Therefore W is equal to, this becomes dw. So minus integration from A to B, Q divided by 4 pi epsilon naught R square into dr. Take the constant outside, minus Q divided by 4 pi epsilon naught, integration from A to B, 1 by R square into dr. What is the integration of 1 by R square? Minus 1 by R. W is equal to, then minus into minus, this becomes plus, Q divided by 4 pi epsilon naught into 1 by R from A to B. Then the resultant expression is W is equal to Q divided by 4 pi epsilon naught into 1 by RB minus 1 by RA. This is the expression for total work done in moving a charge from arbitrary points A to B, right? Okay. Now then W becomes V. Work done is from B to A. So potential from B to A, potential difference from B to A is equal to Q divided by 4 pi epsilon naught into R into 1 by RB minus 1 by RA. We know that work done also equivalent to the potential difference. That's why W is replaced by VBA. Work done is equal to potential difference between point B and A. Got it? Now let me repeat again. Consider a point charge Q at origin O of the coordinate system. Okay. Consider two arbitrary points A and B within the vicinity of the field developed by point charge. Okay. Now the path is selected arbitrarily. Let us consider a point P on the particular path, okay, which is at a distance r from the origin. Now it is required to move a certain distance delta L within the given path. That point is considered as r. So the distance between P and r is delta L. So r is at a distance r plus delta r, that is the differential length increased. Delta r is the differential length increased. These 2 points are named as M and P. Draw a perpendicular MP to the line OR. Since delta L is very small, R and OP are all approximately equal. Therefore, MP is perpendicular to both OP and OR. See, OP and OR. Therefore, this angle becomes theta. Since we have the theta value, cos theta is equal to MR divided by delta L, that is adjacent by hypotenuse. Adjacent length is MR, which is given by delta R divided by delta L. With this equation, we can have the equation for delta R. Now, elementary work done equation is given by this form. Okay, if we substitute the electric field intensity equation in this equation, we left with this form. So if we substitute the limits, then delta L becomes DL, delta W becomes DW. If we integrate all the elementary points from A to B, we are going to get the total work done. Solving the above equation, we will get this form. We know that work done is equivalent to the potential difference, then W is equated to VBA. Got it? Okay, let us move on to the next part. Potential at a point due to a point charge. This is very simple. What do you mean by potential at a point? Potential at a point is moving a unit positive charge from infinity to a particular point in opposite to the electric field direction, right? That is called potential at a point. Now let us use this equation. That is VBA is equal to Q divided by 4 pi epsilon naught into 1 by RB minus 1 by RE. According to the definition of potential, so we need to push the unit positive charge from infinity to a particular point. Now point A is at infinity. Point A is at infinity. Okay. Now when we push that point from infinity to a particular point, then this equation becomes 4 pi epsilon naught into 1 by RB minus 1 by infinity. What do you mean by 1 by infinity? This is 0. This is 0. We left with only this quantity. Therefore, VBA is equal to Q divided by 4 pi epsilon naught into RB. In general, if the point B is at particular point P, then if B is at particular point P, then this becomes general equation for V. V is equal to Q divided by 4 pi epsilon naught into R. V is equal to Q divided by 4 pi epsilon naught into R. This is the general equation for potential at a point due to a point charge, provided that point charge is kept at origin of the coordinate system. Okay, so that is in this form. This is Z, this is Y, and this is X. Charge is placed at the origin of the coordinate system. Then only this equation holds good. What happens if this point charge is not present at the origin, somewhere else in the coordinate system? Then this above equation is going to change. That representation is given like this, special case. Okay, if the point charge is not at the origin, what will happen to this equation? Okay, so let me write here. This is X, Y, and Z. The charge Q1 is somewhere else in the XYZ coordinate system, okay, which is at distance R1. Point, this is the point O. Q1 is placed at a distance R1 from the origin. Let us consider a point P, which is at a distance R from the origin. Now what is this distance? This distance is R minus R1. This distance is R minus R1. Got it? According to the vector algebra we have learnt, this distance is R minus R1. Then what happens to this equation? V is equal to Q divided by 4 pi epsilon naught into 1 divided by R minus R1. Okay. This is the general equation for potential at a point due to a point charge which is kept somewhere else in the XYZ coordinate system other than origin. Got it? Okay, we have seen the equation for potential field due to a point charge, which is when the point charge is kept at origin and other than origin. Now what happens to this potential field equation due to many charges? When many point charges are present, what happens to the given equation? Let me write that. Okay, now what is the equation for V? V is equal to Q divided by 4 pi epsilon naught into 1 divided by R minus R1, right? This is what we have written. Okay, now what happens to this equation? Then V is equal to V1 plus V2 plus V3 plus so on up to Vn when n number of charges present, Q2, Q3 up to Qn. When n number of charges are present, then n number of potentials we are going to get. The total potential is equivalent to the algebraic sum of all these individual potentials. Let me write that equation. Then total potential V is equal to, what is the expression for V1? Q1 divided by 4 pi epsilon naught into R minus R1 plus Q2 divided by 4 pi epsilon naught into R minus R2 plus up to Qn divided by 4 pi epsilon naught into R minus Rn. This is the general expression, right? What are the common quantities? V is equal to 1 by 4 pi epsilon naught is the common quantities. Then we can use summation of Q I varies from 1 to n, right? It varies from 1 to n. Qi divided by R minus Ri. This is the expression for potential field due to many charges. Got it? So in the next topic we can find the potential due to line charge distribution, volume charge distribution, surface charge distribution. Okay? Now let us see potential due to continuous distribution of charges. Continuous distribution of charge in the sense we need to consider all the three cases: line charge, surface charge and volume charge. Now let us go with line charge distribution first. So when we consider line charge distribution in a three coordinate system, okay, x, y and z, okay, consider a line charge distribution, okay, positive line charge distribution in xyz plane, okay. Consider the elementary distance dl dash. This is the elementary distance which we have considered. This elementary distance is at distance r dash from the origin O. Let us choose an arbitrary point P at a distance r from the origin. The distance between the elementary point and P is given by r minus r dash. The distance between P and this elementary differential length is given by r minus r dash. We have seen the same geometry in the previous discussion, right? So we know that line charge density rho L is equal to charge per unit length, differential charge per differential length. What is the charge at this differential length? The charge at this point is dq, differential charge, not the total charge, right? The differential length is having the differential charge. Then line charge density is given by rho L is equal to dq by dl, right? So what is the equation for dq? dq is equal to rho L into dl, okay, rho L into dl. See, dl is represented by dl dash in this equation. Now let me write dl dash here. Got it? So dq is equal to rho L into dl. Now what is the expression which we have derived now for V, which is represented as this form? Vector field is given by q divided by 4 pi epsilon naught r minus r dash, right? So when the charge is placed other than origin, this is the equation. R dash is the distance from the point at which we are measuring the potential field, then this becomes r minus r dash. So what is the charge at this particular point? dq. dq is the charge, elementary charge, okay. Now what is dq? dq is equal to rho L into dlz. Then V, the elementary potential field at that elementary point is given by dq divided by 4 pi epsilon naught into r minus r dash. Then dq is replaced by rho L, represent in this form dl dash, okay. Now how to obtain the total potential field due to line charge distribution? We need to integrate all these terms. V is equal to integration of all the dV components will give us the potential, that is rho L of r into dl dash divided by 4 pi epsilon naught into r minus r dash. This is the expression for potential field due to line charge distribution. Why dl dash is mentioned here? We know that line charge density is not uniform throughout the length of this line charge. Hence, we have different densities at different point on the line charge, hence we can represent it as dlz. That is the explanation for writing dlz here. So this is the total expression we have got for potential field due to a line charge distribution. Similarly, we can go for surface charge as well as volume charge distribution. So what is the surface charge density? dq by ds. What is the volume charge density? Rho v is equal to dq by dv. So if we replace dl by ds and dv successively, we can get potential due to surface charge and volume charge distribution. Surface charge is rho s dl dash divided by 4 pi epsilon naught r minus ds. Okay, this is the expression for volume charge. Rho v dv divided by 4 pi epsilon naught r minus r dash, where rho s is equal to dq by ds, where rho v is equal to dq by dv. By replacing rho l by rho s and rho v, we can obtain this equation by following same set of procedure. This is how we can obtain the equation for potential due to continuous distribution of charges with respect to all the three different cases. Got it? Let us move on to the next topic, potential at a point due to line charge. Okay, so the line charge which we need to consider is of infinitely long line charge, which is positively charged. Infinitely line charge which is positively charged. Okay, consider a point P which is at a distance r from the line charge. Okay, now which produces the electric field E in this particular direction. So this is the another point P dash, another point P dash which is at a distance r dash from this line charge. Okay, this distance is dr. This distance is dr, differential distance, which is in opposite direction to the electric field. The point charge, this is moved from P dash to P in opposite direction to the electric field. That distance is dr, differential distance taken is dr. So we need to push the unit positive charge from infinity to a particular point P, which is impractical. We cannot push or move any charge from infinity to a particular point. That's why in order to avoid that problem, we are moving a charge from P dash to P in opposite direction to the electric field, where r dash is greater than r, where r dash is greater than r. So instead of moving a charge from infinity to a particular point P, we are moving a charge from P dash to P. That corresponding distance is r dash to r. The differential distance taken is dr. Now write the expression for potential. Then potential V is equal to minus integral from infinity to P E dot dr. Instead of dl we have used dr symbol, so E dot dr. Now if I resolve this dot product, then this becomes infinity to P E into dr into cos theta. What is the angle between dr and E? Both are 180 degree out of phase. Therefore, theta is equal to 180 degree. 180 degree means they are out of phase. Both are in opposite direction. Therefore, the angle between dr and E is 180 degree. Cos 180 degree is equal to minus 1. Then the above equation becomes V is equal to integration from infinity to P E into dr. E into dr. Okay. Now, what is E? We know that E is equal to rho L divided by 2 pi epsilon naught into R into A cap R. This is the expression for electric field intensity due to a infinitely long line charge. Then substitute this into the above equation. Therefore, V is equal to integration from infinity to P. What is E? Rho L divided by 2 pi epsilon naught into R. So instead of small r, I will use capital R here, R into dr. Now with respect to this assumption, we cannot move a charge from infinity to P. Instead of that, we are moving this charge from R dash to R. Look at this. From R dash to R, we are moving this. So rho L divided by 2 pi epsilon naught into dr divided by R. The equation has been rewritten into this format. Then V is equal to rho L divided by 2 pi epsilon naught, which is constant, we have taken outside, from R dash to R dr divided by R. What is the integration of 1 by R? 1 by R integration is log R. Therefore, V is equal to rho L divided by 2 pi epsilon naught log R from R dash to R. Okay. Now, how to solve this? V is equal to rho L divided by 2 pi epsilon naught into log R minus log R dash. According to logarithmic laws, log A minus log B is equal to log A by B, right? Therefore, V is equal to rho L divided by 2 pi epsilon naught into log of A by B, that is R by R dash. This is the final expression for potential at a point due to a line charge. Okay. Let us move on to the next topic, relation between electric field intensity and electric potential. What is that relationship between E and V? Relationship between E and V. So we need to establish the relationship between electric field intensity E and electric potential V, which is very, very important in order to solve mathematical problems. Okay. So let us do it. Let us consider two neighboring points A and B, which are located at coordinates x comma y comma z and x plus delta x comma y plus delta y comma z plus delta z respectively. The two points are at distance delta L apart. Now let us write this. A point A and point B, which is at coordinate x comma y comma z, point B at a coordinate x plus delta x comma y plus delta y comma z plus delta z. Okay, this is the coordinate. So these 2 points are delta L apart. The distance between these 2 points is delta L. The potential at point B is greater than the potential at point A. The potential at point A is considered to be V. The potential at point B is considered to be V plus delta V. So point B is at higher potential than the point A. Now we need to establish the relationship between E and V with this particular geometrical consideration. Now the work done, the elementary work done, delta W, in order to move a charge from lower potential to higher potential, in order to move a charge from A to B, is given by minus Q times of E dot dl, right? We know that delta W becomes delta V when Q is equal to 1, right? Then if we move the unit positive charge from lower potential to higher potential, the work done becomes the potential delta V is equal to minus E dot dl. Okay, now dl can be written as dx a cap x plus dy a cap y plus dz a cap z. Now if I substitute dl component into the above equation, then delta V is equal to minus E dot dx a cap x plus dy a cap y plus dz a cap z. Name this as equation 1. Then the potential difference delta V can also be represented as dou by dou x of V into dx plus dou by dou y of V into dy plus dou by dou z of V into dz. So we can represent delta V into this format. If we resolve this equation into their dot product, then delta V is equal to dou by dou x of dou by dou x into a cap x plus dou by dou y into a cap y plus dou by dou z into a cap z into V dot dx a cap x plus dy a cap y plus dz a cap z. Okay, name this as equation 2. See, if I take the dot product between these two, we are going to get the same equation. A cap x into a cap x is equal to 1. Then dx is going to multiply, V comes here, then the same equation comes. Now compare 1 and 2. Compare equation 1 and 2, because LHS is same for both equation 1 and 2. If we compare these two, what we are going to get? See, this component and this component gets eliminated. Then minus E is equal to dou by dou x a cap x plus dou by dou y a cap y plus dou by dou z a cap z into V. Okay, what is this quantity? This quantity is gradient, that is E is equal to into V. Okay, therefore E can be written as minus of vector operator into V. This is the relationship between electric field intensity and electric potential. This is very important for our problems, numerical problems. Got it? Okay, let us solve a problem on the topic which we have learnt. So let me read the problem statement. If the potential field V is equal to 100 into x square minus y square, find electric field intensity E, potential field V at a point 2, minus 1, 3. The coordinate has been given. At this point we need to calculate V. You can ask a doubt. Sir, already V is given. Yes, obviously V is given, but you need to recalculate this V at this particular coordinate 2, minus 1, 3, right? And the equation representing the locus of all points having potential of 300. We need to write the equation at a point where the potential is 300 for all the locus of points. Okay, so this is the problem statement given. We need to calculate three different aspects here. One is E, another one is V at this particular coordinate, and equation representing all the points having the locus of potential 300. Okay, solution. How to solve this? V is given. V is equal to 100 times of x square minus y square. Name this as equation 1. Then potential point P is given as 2, minus 1, 3. What we need to calculate? E. E we need to calculate. V at this point we need to calculate. This is the problem statement. Now we know that E is equal to minus gradient dot V, gradient into V. This is the expression, but we don't know the value of V. So V is given as 100 times of x square minus y square. Let me write this. E is equal to minus, what is gradient? Dou by dou x of a cap x plus dou by dou y of a cap y plus dou by dou z of a cap z into V, that is 100 times of x square minus y square. So no need of having this bracket. Now take this quantity inside. What we are going to get? E is equal to minus of dou by dou x, means take 100 outside. This becomes 2x a cap x minus, so minus 100, okay, 100 has been taken outside, plus this becomes minus 2y a cap y. So differentiation of x square is 2x into 1. Differentiation of y square with respect to y is 2y into 1. Z component is absent, so no need to write that. Then E is equal to minus 200x a cap x plus 200y a cap y volt per meter. This is the expression for E, electric field intensity E. Now coming to this second point, V at a point 2, minus 1, 3. Second component. This is the first component. V at 2, minus 1, 3. Therefore V is given as 100 times of x square minus y square. According to this, x is equal to 2, y is equal to minus 1, z is equal to 3. Substitute these quantities here. Then x square means 2 square minus of minus 1 square. What is the value? 4. 1 square is 1. Okay. Minus 1. What is this? V is equal to 300 volt. So potential at this point is 300 volt. Then coming to the third point, what is that? The equation representing the locus of all points having potential of 300. So what is that equation? So in order to obtain that, if I substitute V is equal to 300 in equation 1, then it satisfies the requirement. This is the equation for the third part given in the problem statement. Okay, if I substitute V is equal to 300 in equation number 1, this part holds good. Understood? Thank you. Okay, let us solve one more problem. Potential is given by V is equal to 2 into x plus 1 square into y plus 2 whole square z plus 3 whole square volt in free space. At a point P is equal to 2, minus 1 and 4, calculate potential, electric field intensity, flux density and volume charge density. Potential means V, electric field intensity E, flux density D and volume charge density, that is rho V. Rho V is equal to gradient dot D. Okay, this is what we need to calculate. Let us go one by one. First one is calculation of potential at 2 comma minus 1 comma 4 x comma y comma z. Okay, now V is equal to 2 into x plus 1 whole square into y plus 2 whole square into z plus 3 whole square. V is equal to 2 times of what is the value of x? 2 plus 1 whole square. What is the value of y? Minus 1 plus 2 whole square. Z is 4 plus 3 whole square. Then V is equal to 2 into 3 square means 9 into minus 1 plus 2 1 square, that is 1. This is 49. What is the final value? V is equal to, what is the value? 882 volt. This is the potential at the given point. Then coming to the second part, B, electric field intensity. We know the relationship between E and V, that is gradient into V. This is the relationship between E and V. Substitute this. E is equal to minus of gradient. What is that gradient? Dou by dou x a cap x plus dou by dou y a cap y plus dou by dou z a cap z into V. What is this? 2 into x plus 1 whole square, y plus 2 whole square, z plus 3 whole square. Now take it inside. What we are going to get? E is equal to minus 2 will be coming outside. Then this becomes dou by dou x of this quantity, that is 2 into x plus 1 into y plus 2 whole square, z plus 3 whole square. Okay, plus this quantity becomes 2 into y plus 2 into x plus 1 whole square into z plus 3 whole square, then plus 2 into z plus 3 into x plus 1 whole square into y plus 2 whole square, right? So if I differentiate with respect to x, y, z into this form, so we are going to, this 2 is common, take it outside. E is equal to minus 4 times of, so we have x plus 1, y plus 2, z plus 3. All these terms are common, we have taken it outside. Then we left with what we are going to get. So 2 is taken outside. Then we are going to get y plus 2 into z plus 3, right? here x plus 1 is taken, 1 y plus 2, 1 z plus 3 is taken outside, we left with this quantity. Then 2 is taken outside, we left with x plus 1 and z plus 3, okay, into a cap x, this is into a cap y, this is into a cap z. Here a cap x, a cap y plus x plus 1 into y plus 2 into a cap z. Okay, substituting x is equal to 2, minus 1 and 4 into this equation, what we are going to get is E is equal to minus 588 a cap x minus 1764 a cap y minus 252 a cap z volt per meter. On substituting x is equal to 2, y is equal to minus 1 and z is equal to 4 into this equation, we are going to get this form. Okay. Now, in order to calculate the magnitude of E is equal to square root of 588 square plus 1764 square plus 252 square. So magnitude of E is equal to 1876.4 volt per meter. This is the second quantity. Then coming to the third part, that is, what is that? Flux density, D, calculation of flux density. Flux density, what is that? Relationship between D and E is D is equal to epsilon naught into E. We know the value of E, we need to calculate D. Therefore, D is equal to 8.854 into 10 power minus 12 times of E. Okay, if I substitute that, then magnitude of D is equal to 8.854 into 10 power minus 12 times of magnitude of E, that is 1876.4 volt per meter. Then D is equal to 16.613 into 10 power minus 9 coulomb per meter square. This is the flux density D. Third part is over. Then last one, that is volume charge density. Volume charge density, that is rho v. See, rho v is equal to gradient dot D. This can be written as gradient dot epsilon naught into E. In other words, this can be written as epsilon naught into gradient dot E. Okay, now substitute here. Rho v is equal to epsilon naught times of, what is gradient? Dou by dou x of a cap x plus dou by dou y of a cap y plus dou by dou z of a cap z dot E. What is E? E we have calculated here. See, this is the expression for E. You can directly substitute this. We can directly substitute this E into this equation. Therefore what we are going to get? Minus 4x plus 1 y plus 2 z plus 3 into y plus 2 z plus 3 into a cap x plus x plus 1 z plus 3 into a cap y plus x plus 1 y plus 2 into a cap z. See, this term has been shifted here. Okay. On taking dot product between these two, look at this. If we multiply these two, if I take dot product between these two, a cap x into a cap x is equal to 1. Dou by dou x of x component. Since we have x component here, x plus 1, the differentiation of x plus 1 is 1, then rest of the components remains as it is. Then rho v is equal to, what we are going to get? Minus 17.67 into 10 power minus 9 coulomb per meter cube. This is the final expression for volume charge density on substituting x is equal to 2, y is equal to minus 1 and z is equal to minus 4 for this particular equation. You need to solve this. Take dot product between these two terms and substituting for x, y, z. So we are going to get this equation, this value. Okay, this is how you need to solve this type of problems. Thank you.